Okay, so we have covered AGN. As you can see, we are really going at reasonably fast pace. I'm trying to do some little calculations here and there. Uh, the aim is actually to build intuition, and to be able to do some basic calculations, and not to go into great details. Uh, so we are roughly halfway through the course. Uh, so now we'll do galaxy clusters, IgM. We will go into interstellar medium, on which we'll spend about a month. Okay. So today, we are starting galaxy clusters. We have actually done a little bit of this here and there earlier in different forms. So there'll be a little bit of repetition. So things like violent relaxation, things like dynamical friction, right? Most massive galaxies in a galaxy cluster sort of sink to the bottom of the potential well. And that's because of dynamical friction. If you recall this Chandrasekhar's dynamical friction formula, the time for losing momentum is proportional to 1 by m. So more massive star or a more massive object has a bigger wake, which tries to slow it down. And so the quickly most massive members of a gravitating system sink to the bottom of the potential well. So the same thing applies here. Violent relaxation, the fact that formally the two-body relaxation time is pretty long, but still a lot of these systems look relaxed in the sense that they are spherical, have random velocity distribution of galaxies and so on. So, galaxy clusters is also something that my research has been on. So, this may have a little bit more stuff, somewhat different. I think so. No, not. Yeah, that's. Let me just check. Yeah, I think there is a. That's okay. So I'm sort of still following that book, the second book for our course, but it will have some material which is, outside that. But not very sophisticated stuff. Okay. So this is sort of like setting the context, right? The CMB gives us a snapshot of tiny perturbations in the matter density or the temperature of the universe at very early times. Those are supposed to come from the quantum fluctuations in the early universe. And they are the seeds of tiny fluctuations, which because of self-gravity or gravitational instability become more and more. Universe evolves in time. Okay, so here is actually what is shown here in this slide is snapshots at 3 different cosmic times from a n-body simulation. So there are cosmological galaxy formation simulations of different kinds. Okay, so the earliest simulations did not evolve baryons at all. What they did was, okay, most of the matter in the universe is in form of dark matter, and the only interaction that dark matter has is gravitational. So what they say, okay, let's populate the universe with tiny fluctuations early on, and let there be self-gravity, let there be a background cosmological evolution, in the sense that there is a background evolution in which galaxies are moving away with respect to each other in a Hubble flow, right? If you start with that, small fluctuations in a Hubble flow, this is how the evolution looks like. So the redshift of the CMB is 1,100, very early times. But, there things are very linear, like 10 to the minus 5, right? Delta rho over rho is typically 10 to the minus 4, 10 to the minus 5. So those tiny perturbations grow with time. So this is at redshift of 6, so much later than that. So I assume that you have done a little bit of FRW cosmology in your fundamentals of astrophysics. A little bit, all you need is how the scale factor of the universe, goes with time. So there is a simple mapping depending on the cosmological parameters between the redshift and the age of the universe, for example. So all that just comes from homogeneous isotropic background evolution of the Friedmann equations. Okay, so this is redshift of 6. What is shown here in color is 3D distribution or a 3D rendering of dark matter density, right? So at redshift of 6, you can actually see slightly more overdense regions and slightly underdense regions in dark matter field. So these are actually inherited from the CMB. If you extrapolate it all the way back to very high redshifts, you'll see that the high densities here correspond to high density in the CMB map. So you can actually sort of imagine it like, you have perturbations in the higher density, higher temperature regions of the CMB were slightly more gravitating than their surroundings, and they sort of collapsed and gave rise to these overdensities and underdensities. Okay, so there is like a rough mapping of very high redshift density fluctuations and present day fluctuations as seen in distribution of galaxies, for example. So you can actually see it from this limited evolution in time that, if you look here, there is slightly higher density, right, compared to the rest of it. So with time, what happens is more and more mass, and at the present time, which is redshift of 0, you can see that there is like a halo formed here, which is at the intersection of these cosmological dark matter filaments, right? So this is what happens in matter density, but matter density at these large scales is faithfully traced by distribution of galaxies. So if you want to convert this into a picture of something that you will observe in the night sky, is to zeroth order, just replace these high density in dark matter by higher probability of getting galaxies. Right? But that's not precisely correct. Dark matter is not traced perfectly by galaxies, and there is something called a bias factor. Basically, what is bias factor basically tells that what is the excess probability of having galaxies compared to a dark matter halo. We'll not go into that, but this is like a very sophisticated area too. Like just how structure forms and evolves because of this gravity and cosmological evolution. And there is some powerful formalism called this Presch-Schechter formalism, which maps the fluctuations in the CMB to the abundance of galaxies in the local universe, right? So as I said, the high density peaks in the early universe can actually be mapped to most massive clusters in the local universe. So this whole mathematical formalism of calculating the mass function of halos and its evolution with time or redshift is called this Presch-Schechter formalism. Okay. But so this is sort of an analytic formalism, and it has its own limitations, but it's very good analytic model. But the state of the art is these nonlinear n-body simulations, snapshot of which is shown here. Now, people have done not just dark matter, but they have included gas, stars. So you can actually make, a mock galaxy catalog from your simulation. So the modeling has become really sophisticated. Okay. So this is from simulation. So what happens is you have this higher density region here, which is marked in this circle. This is the dark matter view of something called a galaxy cluster. The galaxy cluster is the strongest, the deepest potential well in the local universe, and it pulls matter into it because of its strong gravity. So all these galaxies which are in these filaments over time will just fall into this potential well. Okay, so you can actually think of galaxy clusters as these big metropolises like Mumbai or Delhi, where people from rest of the country, the voids and so on, all migrate into. Okay, so these are sort of like the highways in this universe. And you can also see that the distribution of light is much more here. There are many more galaxies in the clusters. But clusters are also very rare. So in fact, the analogy actually is exactly this metropolis or the city analogy works. So there are not many Mumbais or Delhis in India, right? There are only a few, and they have very high population. But most of the population of the country is not in this metropolises. They are in the tier 2 or tier 3 cities. Those are called groups of galaxies. So the equivalent of them is groups of galaxies. Like our Milky Way is part of the local group of galaxies, and M31 Andromeda and Milky Way are part of this galaxy groups. So galaxy clusters are exponentially rare. That's why there aren't many of them. Most of the galaxies in the universe fall into these things called groups. So we'll actually come to that. Now this on the left is the distribution of galaxies in a patch of the sky as produced by Lick catalog of galaxies. So you can actually see the galaxies are not perfectly uniformly distributed. Right? They are not like distribution of molecules in a chamber. There are over densities like this, and there are under densities like this, voids. And these are sort of clusters and groups. And this is an observational example, right? So this is, you're looking at a patch of the sky. This is a projected map, right? You're looking at the part of the sky and everything along that sight line, whether nearby or far away, falls in the same region in the sky. So, so this is like a projected map. And every point here is a galaxy, essentially. Every bright white point here is a galaxy. This is another view of such a such a distribution of galaxies. This is like only a 10 arc minute by 10 arc minute region, a small region, smaller than the size of the moon at night. So this is a really tiny patch in the sky. This is all sky distribution of galaxies because this is galactic coordinates. So you can actually see the mid plane of the galaxy. You don't really, you don't see a lot of galaxies because it's all absorbed by the dust and confusion and all that. So you just sort of try to avoid this for galaxy studies. But then you can actually see again that there is an overdensity here, and so on. So these are, I mean, in 80s and 90s, people did these massive galaxy surveys to understand the large-scale structure of the universe. This is what I was actually telling you, that the Milky Way galaxy, which is here, is part of something called the local group. Right? So this is our Milky Way. This is Andromeda galaxy. Where is it? And this is Andromeda galaxy. Milky Way and Andromeda, respectively, most massive members of their little domains. So Andromeda is the most massive, and they have these dwarf galaxies and smaller galaxies which go around them. Similarly, here we have a large Magellanic Cloud, small Magellanic Cloud, and other and irregulars and whatnot going around each of them, and the two of them, Milky Way and Andromeda, are actually moving towards each other. And so this region, which is of order like a megaparsec, is the local group. And this is the local group center of mass, the local group barycenter, roughly in the middle of Milky Way and Andromeda. They're roughly equal size. Some of these galaxies are extremely hard to find. Some of these dwarf elliptical or dwarf spheroidal galaxies have extremely tiny surface brightness, and suppose they are like close to the galactic center, towards the center of our galaxy, it's very, they're just lost in the stars of the halo of our Milky Way and the bulge of our Milky Way. So some of these dwarf galaxies were discovered like, as late as 10 years ago. So these are some of the images from the textbook. And as I already mentioned, most galaxies in the universe exist in groups. Okay. So one thing that I actually wanted to show but did not have the slide on, which I realize now, is something called this. Do you recall this luminosity function of galaxies, right? Number of galaxies as a function of luminosity. How many galaxies are there between luminosity L and L plus DL is equal to phi L DL, right? So you can actually do this luminosity function for galaxies. And if you do that, what you find is it sort of fit well by this Schechter function. So like L to the -2 or some power law, and then an exponential cutoff. Okay, so in that, if you do the same exercise for mass distribution, not the luminosity distribution, you roughly get a power law and exponential cutoff. So what it means is that the most massive halos are exponentially rare. And these most massive halos correspond to the host halos of clusters of galaxies. Okay, whereas the power law part and the L star or M star, where most of the mass of the galaxies reside, are little lower mass compared to the cluster mass, and they correspond to the groups. So groups are very interesting because that's the typical environment in which a galaxy like our Milky Way exists in. Environment plays a very big role in the properties of galaxies. For example, most member galaxies of clusters are elliptical red and dead galaxies with not a lot of star formation. So the group environment, because of being so higher density, the probability of galaxies, having strong encounters with each other increases, and that converts disk galaxies into red and dead elliptical type galaxies. So the environment plays a big role in the observational appearance of galaxies. And so galaxy clusters were first identified in optical because, optical is where we had the best instrumentation, right? Photographic plates and whatnot. Even by eye, you can see. So optical is far ahead compared to all the other, instrumentation in all other wave bands, because that's what we have all been used to. There's a big consumer market also for the optical photography and so on. So that's why galaxy clusters were seen first in optical images. So this is a group of galaxies observed with Subaru telescope on Mauna Kea. This is a telescope in Hawaii, a big ground-based telescope. The right panel displays the clusters of galaxies obtained with WFI at ISO 2.2-meter galaxies. This is a galaxy cluster. You can actually see there is an overdensity of clusters compared to, say, this region, of galaxies compared to this region or this region. And a lot of these galaxies are massive red and dead galaxies. They're red in appearance. This is a group, this is a cluster, and you can actually see in the group you do have galaxies which show, like, spiral arm features and interactions and some star formation. But here it's essentially most of these galaxies are quenched. So you will hear this term quenched a lot of times when you look at the galaxies literature. Quenching means cessation or stopping of star formation. So star formation rate becomes small. If in a galaxy the star formation rate decreases by to an imperceptible level, that's when you say that the galaxy has been quenched. And after a while, after 100 million years after that, you only have old stars. Okay, so these are mostly quenched galaxies in galaxy clusters. Okay, galaxy clusters are actually very versatile objects. You observe them in almost all wavebands. Galaxy clusters emit in radio. Most massive elliptical galaxies are in galaxy clusters. So all these giant radio galaxies occur profusely in galaxy clusters. Galaxy clusters are seen in millimeters through something called this Sunyaev-Zeldovich effect, SZ effect. They are seen in optical, because you see the member galaxies. In optical, you also see the lensing of background galaxies, as you can see in this image. This is an HST, Hubble Space Telescope image of a galaxy cluster, Abell 2218. So Abell catalog of galaxy clusters is a famous optically selected catalog of galaxy clusters. So you can actually see that there are arcs of background galaxies here, here, here. So this is because of strong gravitational lensing of background galaxies by the foreground, this massive cluster, right? If you recall your little bit of lensing that we did, that strongly gravitating objects like black holes and massive dark matter halos cause the light from the background sources to get deflected and magnified and images to be distorted. So this is an example of that. So by modeling the distortion of the background galaxies, you can actually model the mass distribution of the foreground cluster. So this is one way of measuring the gravitating mass of a galaxy cluster, right? Because we all know now that most of the mass in the universe is not in stars and stuff. It is in this dark matter which you cannot see. But gravitational lensing is sensitive to the total mass, which is dominated by dark matter. So this is gravitational lensing is a way to constrain the gravitating mass or the dark matter mass distribution within galaxy clusters. So in optical, we see galaxy clusters. X-rays, they are one of the brightest sources in X-rays. Gamma rays sometimes through AGN, but not so much. So basically, they are in all wavebands except perhaps the highest energy waveband. They emit, galaxy clusters emit. Now this is a plot of the mean cluster mass. So determining cluster mass is tricky, right? Because you don't. A very reliable way of measuring cluster masses is by modeling gravitational lensing. But apart from that, you have to do some sort of a genes modeling. If you recall, we had used this genes modeling. Clusters are spherically symmetric systems, so using sigma square and all that, you can actually, or applying virial estimate, you can get a sense of mass of galaxy clusters. So the y-axis on this plot is mean cluster mass. X-axis is something called richness. So richness is a property of a galaxy cluster which you can actually define from your optical surveys. So so richness is a mark of how many galaxies do you have within a megaparsec or some distance or some angular distance on the sky, which corresponds to some physical size. How many galaxies do you have above a certain luminosity? Right, so above a certain absolute magnitude. That is x-axis. So what you see is the richer the galaxy cluster is, the more massive it is. Right, so it's sort of expected, right? You have a larger number of bright galaxies means that the cluster is more massive cluster. So this is from a survey which did this lensing analysis of galaxy clusters and just counted the number of bright optical galaxies. And so this, you sort of see a correlation like this. It's almost a one-to-one relation. So galaxy clusters are also useful in cosmology. Or dark energy, right? You can actually affect the abundance of clusters. So by counting the number of clusters as a function of their masses, if you can get that, you are indirectly constraining the cosmological parameters, specifically the dark energy, things like lambda and the equation of state for dark energy. So this is a number of clusters with, so this is like some sort of a cumulative distribution function or the distribution function. N gals is number of galaxies within some radius of a halo. So more the number of galaxies, the richer this cluster is, right? I had introduced this concept of richness. The more the number of member galaxies of a cluster, the richer it is, more massive it is. So you can actually see from here that most massive clusters are rarer, much rarer than less massive clusters. You can actually see it from here. Right, so these are all the clusters and groups with this number greater than 10. Now this is the same clusters, number of clusters, and you define cluster to be something which has some n galaxies, which is greater than some threshold number. So all the galaxies which are on the right of this. So number of clusters as a function of redshift. And here you see that it is using photometric redshift. So there are two ways of measuring redshifts. One is just photometric. So basically you look at these broad bands, U, B, V, and just see roughly what redshift this galaxy is. It's not as accurate. The other is spectroscopic redshift, when you actually have spectra and you can see strong lines and know the redshift exactly. So photometric redshifts have somewhat higher errors and are less reliable compared to spectroscopic redshifts. So one of, actually, if you have been following the recent literature, this James Webb Space Telescope has been finding very, bright galaxies at very high redshifts. For some of those galaxies, the redshifts were photometric redshifts, and for at least some of them were found to be lower redshift galaxies, just that their photometric appearances came out to be indicating very high redshift. They were actually galaxies which were much closer. So photometric redshifts are not as reliable. So this is the solid curve is the expected redshift distribution for a volume limited survey with the sky area of SDSS at a given mean number density of 2.3 times 10 to the minus 5 h cube megaparsec to the minus 3. So this is the number of clusters within a redshift z. So, you know, as you go to higher and higher redshift, the numbers should increase. And this is the expectation from the volume limited survey. So, you know, there are two kinds of surveys, right? One is flux limited survey. So a flux limited survey of galaxies or clusters or whatever is the following. So you say, I will observe all the galaxies which has a flux greater than something. If you have a flux limited survey, you are seeing the most luminous galaxies to much larger distances. The lowest luminosity galaxies you're only seeing nearby. So you're covering a very small volume for low luminosity galaxies and a much higher volume for high luminosity galaxies. So if you do statistics based on a flux limited survey, you will overwhelmingly have more luminous galaxies, right? Because you're looking deeper because they're inherently brighter. So flux limited survey are a little they are not ideal for doing statistics. What you need instead is something called a volume limited survey. What you say is, I will see all the galaxies till this distance with a luminosity greater than something, right? And I'll not count any of the galaxies which are bright and I can see them, but they're beyond this, so that I have a fair count of galaxies of different luminosities. Okay, so this is a volume limited survey, this max BCG survey. Anyway, this is just concepts, more observational, but it is useful to know the meaning of these concepts. Right, so if you have a new object discovered, the first thing that people do, and if that object has a redshift, the first thing that people do is calculate the number of objects with flux greater than a limit, right? So you want to draw a PDF. So let's see. Right, so flux limited survey. So suppose you have number of objects with a flux less than f, right? So if you're here and so this is some distance, and you have objects which have uniform luminosity, let's say, right? So the flux is equal to luminosity by 4 pi d L squared or d squared. DL is something called the luminosity distance. It becomes important when you are doing, when you're looking at high redshifts. But for the nearby universe, DL is the same as normal distance. Now, if you have a uniform density of objects which are emitting, so the number that you expect within, so if you have a flux limit of your survey f, right? So the number of objects that you expect number should be proportional. So basically you'll observe everything within this distance d, right? Because they are all brighter than flux f. So this is your f. So so the number is proportional to 4 by 3 pi d cube, and this is proportional to, right? So this dl and d are the same. So d cube is proportional to f to the minus 3 by 2, right? So number of galaxies with flux less than f versus f, you expect this on a log-log plot to have a slope of minus 3 by 2 if all these objects have the same luminosity and if they have the same spatial, they have a uniform spatial distribution. So the first thing that you do is, okay, I'm collecting all the stars. So this is a very observationally oriented thing. So what you do is you look at, okay, let's take some flux f naught, let's take flux 10 f naught, and so on, and just count the number of objects which are less than that flux, right? If it goes like f to the minus 3 by 2, you're saying that these sort of are nearby and they have a uniform distribution. If you see variations from this, you can say that, oh, you can change one of these assumptions. You can say that they are not uniformly distributed, or they don't have all the same luminosity, right? So things like that. So this is the first thing. A lot of, for example, when you get something like the GRBs, gamma ray bursts, right? So you just say, okay, with this flux in my gamma rays, how many GRBs do I have? And just make something like this. And if this varies from minus 3 by 2, you get some hint on what these things might plausibly be. Okay, so this is clear, right? It's a very, very simple argument that I'm making, is that if you have a flux limit greater than f, you are only seeing, and if all these objects have the same luminosity, you are only seeing objects within this distance, right? And the number of objects in that distance is proportional to d cube, which is f to the minus 3 by 2, because d is f to the minus 1/2. Okay. Anyway, so this is one thing. No, it does not, because GRBs are also cosmological and stuff. So this is, you will see this very, very commonly. That's why I wanted to mention this, especially in the older literature. Well, over this. I want to minimize this window. Okay. I have stopped sharing. No, I don't want to do that. Okay. First, I want to minimize this. Then I want to play this. Okay. Okay. So the other nice thing about galaxy clusters are they're basically spherical halos, and they are something called what follows a self-similar scaling. So galaxy clusters are, especially in dark matter view, are essentially scaled down versions of each other. So if you change the mass of a galaxy cluster, you just sort of reduces size and they can just be put on top of each other. They are self-similar objects. Okay, so they are like extremely simple objects, and they, because of that property, they form a class of, standard halos. So here is a plot of velocity dispersion of member galaxies in a galaxy cluster. So you have a galaxy cluster. There are like 20, 50 to 100 to 1,000 galaxies in this. You measure the velocity dispersion. So the line of sight velocity dispersion. So the central galaxy of the cluster, its redshift, so that's the cluster's redshift. And now some of the galaxies are moving towards us, moving away from us, just like what we did for globular clusters, right? The member stars of a globular clusters have a velocity dispersion of order 5 kilometer per second. Here, the velocity dispersion of member galaxies of a galaxy cluster is around 1,000 kilometer per second. So these are extremely gravitating object as compared to, say, a globular cluster or a Milky Way, which has a rotation speed of 200 kilometer per second. So this velocity dispersion reflects the deeper potential well. So if you plot the velocity dispersion as a function of number of galaxies, this is richness again. So you see that there's a nice scaling here. And this scaling is not linear. The velocity dispersion goes like 1/3 power of this. Okay. Now, this 1/3 power is easy to understand from these self-similar scaling arguments in the following way. Galaxy cluster halos are self-similar. So essentially the argument is the following. So if you have a big galaxy cluster or a small galaxy cluster or a halo, right? So this has a mass. So, this has some radius, and so m by 4 by 3 pi r cube, which is like the mean density. If m is the mass of this halo and r is the size of this halo, this is actually constant. So this is how clusters are defined, and this is how clusters call a lot of these dark matter halos have a rotation curve which is flat. For a flat rotation curve, right, Vc squared is Gm by R. If this is flat, then what it means is the mass is proportional to R. So as you go farther and farther from the galaxy cluster center, you have more and more mass. So how do you define the size of such an object, right? There is no edge to this. As you go out, there is more mass, more mass, more mass. But this cannot go on forever, right? You cannot just have mass increasing with radius forever, because you will run out of mass in that case. So what happens is there is something called a model called spherical top hat collapse. In which what you say is that these galaxy clusters are patches of the universe which initially were very low densities, and so everything was moving away in the Hubble flow. But since they're slightly over dense, at some point they start getting pulled by their gravity and they decouple from the Hubble flow. Okay, so so you imagine this region, a spherical region, which was undergoing Hubble expansion, but it was over dense. So if you just plot like the distance from the center of this R as a function of time, initially this just follows Hubble flow, right? But eventually what it does is it sort of realizes that it's gravitating and it sort of falls back. It's like throwing up a stone, right? It sort of goes up, reaches a maximum distance and falls back. So this radius at which it reaches its maximum distance is called the turnaround radius. And when it falls back in, essentially it sort of like has the same velocity. It's this is done in like approximations. Okay, so what happens is so these shells which are going away, so the outer shells turn around later on, right? The inner shells, so there is more mass at, so the universe forms hierarchically, right? The smaller objects form first. The lowest mass galaxies form first, and the mergers of low mass galaxies from bigger mass galaxies, mergers of galaxies and their dark matter halos forms groups and clusters. So you can actually think of it as the smallest regions overturning first, collapsing first, and the larger regions collapsing after that in this spherical top hat model. And what happens is, so G M by R, this is gravitational energy per unit mass. If R is some radius, plus V squared by 2, this is equal to the energy per unit mass, right? And if the shells do not cross each other in this spherical top hat model, we assume that all the shells, if there is a shell inside, it always remains inside because it sort of collapses first. The outer shells collapse later. So this is a constant. So so when you set velocity is equal to 0, right, at R turnaround minus gm by R, so velocity is 0 is equal to E. So R turnaround, and energy is negative, right? This is a gravitationally bound system, so the total energy is negative. So this is the turnaround radius. Now, when it falls back in, and mass remains constant because all the shells which were inside are still inside, so mass remains constant. So the velocity will just be like a, whatever the velocity was here at this height will be the velocity here, because if R is the same, energy is conserved, so V will be the same, right? At some point, the velocity V squared is minus gm by twice R R delta, let's say. So at some point, the velocity becomes equal to minus gm by 2 R delta, where R delta is the size of this relaxed object, right? So this is nothing. So this is like applying virial theorem, right, for a static, stationary spherical distribution of matter. So this is your velocity squared, and R delta is this is basically the size of your galaxy cluster. Okay. Sorry, this is plus, right? Because this is right. So this is the total energy from virial theorem. Yes, total energy is minus a half of the kinetic energy, and that gives you this, right? So this is the radius at which your halo virializes. So at this radius, so here the shell turns around, it is still falling in, and at some point its kinetic energy becomes of order this minus half of the potential energy, and that's what, when you say that it has virialized, essentially what happens is these collapsing shells encounter the halo, and then it just gets violent relaxation. It sort of isotropizes its radial velocity into three-dimensional, isotropic random velocity. So this process is called virialization. This R delta is called the virial radius. Okay, and if you do these calculations properly, it turns out this R delta is the radius within which the size of the halo is radius within which the average density is delta times the critical density of the universe. Okay, and this delta, if you do this spherical top hat calculation properly, is around 200. So R200 is sometimes used as the radius of a cluster. Right, R200 is radius around the cluster center within which the mean density is 200 times the critical density of the universe. Okay, and this is motivated by the spherical top hat collapse, because these systems have mass which goes like proportional to R, if you just take that literally, but that cannot be like that cannot go on forever. At some point, you will encounter shells which have not started falling back in. So you must run out of this R M going like R behavior, and you run out of it around at this radius where the mean density within which is 200 times the critical density of the universe. So let me actually tell you a little bit more on this. So what is the critical density of the universe at the present time? So the critical density of the universe is nothing but 3h0 squared by 8 pi g, right? If you do these FRW solutions, right, the homogeneous isotropic universe evolution solutions, if the density of the universe is equal to the critical density, the universe is flat, right? It has, and that is what our observations are suggesting, that the universe is flat. Right. So what I am saying is the cluster mass M200. So this 200, as I said, just comes from this spherical top hat model, and it's a rough estimate, like so M200 is just 200 times the so rho CR naught 4 pi by 3 R200 cube, right? Mass divided by the volume of the cluster is 200 times the critical density of the universe. So this is what your R200 is for a given mass. So this is the relation between the mass and the radius of the cluster. This is a constant, right? This is just this. So this is what motivates the self-similar models for halos. So what it just says is that essentially, if you make a plot of rho versus R, a log-log plot, and if you scale R by R200, then all these essentially fall on top of each other, right? Because M by R200 cube is the same irrespective of what your M is. So to zeroth order, if you are able to make the mass density profile for a halo, they are, just stretched or compressed copies of each other. So this is the self-similar model. So, for example, you have this sigma squared, right? So sigma squared. So from virial theorem, 3 by 2 sigma squared is G M by. So you're applying This is the kinetic energy. This is the negative of potential energy minus Gm by R. Gm. So this is per unit mass that I'm applying. So this gives you, right? And from here we know that R 200 is proportional to m to the 1/3, right? So you can see that sigma squared is proportional to m to the 2/3, right? So sigma is proportional to m to the 1/3, and mass is proportional to this richness that I was telling you. That's why this velocity dispersion is proportional to m or n to the 1/3, because these are cell-similar systems. So the more massive galaxy, so if you have, say, a 10 to the 13 mass halo and a 10 to the 15 mass halo, right, or 10 to the 12 and 10 to the 15 mass halo, the 10 to the 12 mass halo will be m to the 1/3, so 10 times smaller in size. So galaxy clusters are about 2 megaparsec. Their R200 is about 2 megaparsec. Our Milky Way lies in a halo which is 10 to the 12 solar mass. So 2 megaparsec divided by 10 is 200 kiloparsec. That's about the virial radius of the Milky Way. So the halos are sort of scaled down versions of each other. That's about dark matter halo. Okay, so that's why you have this. This sort of is consistent with the this self-similar model. So the figure on the right is the co-moving number density of clusters in the Max BCG catalog. So co-moving number density. So at a lot of places you see that whenever you have megaparsec, it appears as megaparsec by small h. Do you know why that is? This small h is this Hubble parameter relative to, say, 100 kilometer per second. Why does this appear as megaparsec per h and not just megaparsec? No. That's right. That is correct. H. But why is there Hubble parameter going here? Because we don't know the distances directly. All the distance, so V equals HD. So D is equal to V by H. So the scale sizes are all dependent on your Hubble parameter, and it goes like 1 over H. So the volume should go like 1 by H cube, which is what it is. So yeah, so that's why the small h will be floating around in these formulae. So this is co-moving number density, number of galaxy clusters per unit co-moving volume. So co-moving volume, you have done a little bit of FRW cosmology, right? So if you have Hubble expansion, right? So the lengths are all expanding with time, and so if you had say 100 galaxies within this volume and you just were doing Hubble expansion, the same number 100 will be stretched over a bigger size at a later time. So what you do is you don't take this effect into account when you're counting galaxies. You say that they're just sort of stretching by Hubble expansion. So the present time, the scales are all compressed and put in past, so that this just Hubble expansion is taken out. When you're using co-moving coordinates, you take out this trivial, in some sense, Hubble expansion. Okay. All right. As I said, you can use this Jeans equation to get the mass estimate or the virial theorem. They are essentially the same things. Jeans analysis is a little more sophisticated way of doing it if the velocities are not isotropic and so on. So this is the Jeans equation. We have actually seen this already. For a spherical distribution, if you have a spherically symmetric distribution of density, and the potential is also spherically symmetric, then you don't have a mean velocity in that case, right? Remember this f, the distribution function, because of these symmetries, have certain dependence on your integrals of motions, right? So in a spherical potential, your magnitude of L is conserved. So that's why you should, if you have a self-consistent distribution function of that kind, you should not have mean flows. So based on all that, this is the Jeans equation. So basically the radial force balance. If you manipulate it, this is what you get as the expression for the enclosed mass. And this is the gravitating mass. This is all the mass there is. Not just the mass in stars, but this includes the mass in dark matter. So this is why, so there was this, in the exam, the last problem was based on this. So some people actually used virial theorem as well. But when I framed that question, I had this in mind that this is, there can be dark matter in there. Most of the mass can actually be not in the stars that we're talking about, but in dark matter. So in that case, this equation applies, and this is what you get. So this is the slope of logarithmic slope of density, logarithmic slope of sigma squared, and this anisotropy parameter. And all these things are order unity. Okay, so and if you ignore this, you just get your virial estimate in any case. So if you plug in the numbers for galaxy cluster, if you recall, sigma was about 1,000 kilometers per second for a massive cluster, and R is like R200, right? And that's about 2 megaparsec or a megaparsec. So if you plug in the numbers for typical velocity dispersion and the sizes, you get a cluster mass of 10 to the 15 solar masses. Now, if you count all the member galaxies and count all the mass in the stars, you get about 100 times m star, right? M star is like mass of the Milky Way in stars, which is about 10 to the 10 solar masses. So this is only about 10 to the 12 solar masses, whereas the gravitating mass is 10 to the 15 solar masses. So what it means is that there is a factor of 100 larger mass than what should be there if you just had stars accounting for the mass. So this is, in 1930s, this was actually first noted by Zwicky, who found that the velocity of these member galaxies is much, much faster than what would their stellar mass suggest. So this is the first evidence of dark matter. And like in most cases, Zwicky was far ahead of his time. So he's one of the astronomers who did these fundamental discoveries. The fact that like neutron stars are formed in supernovae. The fact that cosmic rays are accelerated at supernova remnants. All these were sort of, hypothesized based on observations by Zwicky. Okay. I briefly mentioned that the appearance of galaxies depend on the environment in which they exist. So, for example, galaxies in a cluster are more likely to be elliptical galaxies than those in the field. So field galaxies means that they are not in a very dense part of the universe. Okay, so it's sort of opposite of being in a cluster. The ellipticity fraction, the fraction of galaxies which are elliptical morphologically, is higher for a relaxed cluster. So what is a relaxed cluster? A relaxed cluster is a cluster in which you don't see evidence for tidal tails and things, right? It does not show evidence for recent mergers. You don't see like two very massive galaxies sort of in collision. So the relaxed cluster is one in which it is already sort of settled down, and there is a roughly spherical distribution of stars, of galaxies. So these are some of the properties. So relaxed clusters have a CD, this central dominant galaxy, which is like a S0 type galaxy, right? You have almost spherical looking thing, which has like a disk. So something in between the elliptical galaxies and the disk spiral galaxies, these S0 galaxies. And within clusters, there are almost no spiral galaxies. So yeah. And there is this morphology density relation within clusters. So morphology is whether something is elliptical or disky, and density is the local density of galaxies around that galaxy. So the density of galaxies is higher in clusters because there are many more galaxies in galaxy clusters. So here is a quantitative plot of fraction of a population of galaxies as a function of distance. So the fraction of galaxies of different types in a sample of 6 clusters plotted as a function of radius. So this is a function of radius. So let's see, these circles are elliptical galaxies, these are S0 galaxies, and these are spiral and irregular galaxies. So towards the center of the cluster, the number of spiral galaxies sort of go down on average. The number of S0 galaxies go up, and the number of elliptical galaxy is somewhat going up. Right, so this is this environmental dependence that I was telling you about. So spirals become rarer in galaxy clusters. The same data can actually be looked at in this way. So this N is the local projected galaxy density. So number of galaxies per unit area, for example. Okay. So towards the cluster center, you have a very high density. So these would, or is it not? So yeah, so this, the high value of N is the center of galaxy clusters. And you can, and this is a log plot, this is log, this is linear. So this number is the smallest, the number of spirals is smallest towards the center of the cluster and increases towards the outskirts. Similarly, in the higher density regions, the fraction of ellipticals is higher, and this is the fraction of S0 galaxies. So these are these environmental trends. And yes, N is this local projected galaxy density. So total number of galaxies per unit area, projected area. So if you look at this kind of a thing, you see the projected density is high here, where there are many galaxies, and you can actually see by eye that everything there is elliptical. As you go here in the outskirts, you have more spirals. So this is based on 6 clusters. Okay, so that was about the optical observations of galaxy clusters. There is a very popular model for the dark matter profile, for density profile for dark matter halos, and that's called the Navarro, Frank, and White profile, or NFW profile for dark matter halo. This is how the density of a halo looks like. So this is density. This 3h0 squared by 8 pi g is the critical density I just sort of mentioned. And this 1 plus z cube omega matter is the matter density as a function of redshift. So basically this is the, this factor, the prefactor is just the matter density in the universe as a function of redshift. So, in galaxy clusters, sometimes you use, in the definition, sometimes you use that it's the radius within which the mean density is 200 times the critical density. Sometimes you use the fact that it is 200 times the mean density of the universe. The two are different because not all so this definition uses this omega matter, the definition. But here is the, this is the prefactor, and then this is the profile. So 1 by x at small values of x, and 1 by x cube at large values of x. So so this is motivated from these n-body simulations, dark matter only simulations. And if you look at the density profile of a bunch of these halos, what you find is, this 1 by r at small radii and 1 by r cube at large radii provides a reasonable fit for most halos. Right. So this delta C is some sort of a normalization constant, and you can obtain it by using the fact that the size of the cluster is such that the mean density inside it is 200 times the critical density or the mean density of the universe. So here is delta C in terms of this capital delta C, which was 200. I told you that this is the radius within which density is 200 times the mean density of the universe. And C is something called a concentration parameter. So there are only two parameters in this NFW profile. One is this overall normalization. The other is this C, which just sort of defines how centrally concentrated your density profile is. So let me actually just graphically draw NFW density profile. So this is rho, say normalized to the critical density as a function of R by R200. Okay. Now, in this parameter space, they all, if they are self-similar perfectly, they all fall on top of each other. Right? That's the nice thing about the self-similar model. So this is a log-log plot again. So at small radii, this goes like r to the minus 1. At large radii, it becomes r to the minus 3. And then there is a transition. This is how it looks like. And if you have, say, some sort of a value of concentration parameter, a more concentrated halo would be something like this. You can actually see that this profile has a value of C which is higher. So it was like 1 over R, 1 plus CR squared. So this dashed line has a higher concentration. The matter is more centrally concentrated. Right. The other nice thing about this NFW profile is that basically this is very analytically tractable. So you can actually get the self-consistent potential due to this density distribution, right? In general, if you are given a density distribution, it's quite hard for a general density distribution to get a potential, right? The inverse problem is fine, right? You just have to do a del squared. But given a density, to find phi is trickier. But for this NFW potential, you have a gravitational potential which goes like log 1 plus Cx by x. and X is this R by R 200. Oh. So you have phi, you have enclosed mass as a function of R, which actually goes like R, roughly like R at large radii, which gives you flat rotation curve. So this actually has a lot of nice properties, and it also matches with uh, dark matter simulations. Okay. Galaxy clusters, as I told you, can be useful as cosmological probes. That is, they can constrain the cosmological, these lambda CDM parameters. Uh, so I already mentioned dark matter uh, was invoked by Zwicky as early as 1930s because of the fast motion of member galaxies in a cluster. Uh, so there are a bunch of different ways in which galaxy clusters are used as cosmological probes. Galaxy clusters, the other nice thing about galaxy clusters is that they are baryonically closed. That is, if you go and look within R200 of a galaxy cluster, you can account for all the baryons. This is not true for lower mass halos. Like in the Milky Way, you cannot account for most of the baryons, which should be there according to the standard abundance of baryons relative to the dark matter particles. Uh, the other way in which you can use galaxy clusters as cosmological probes is you can use BCGs, the brightest central galaxy of a galaxy cluster, as a standard candle. This is not a very good standard candle though, so this is not that great. The best way to use galaxy clusters as cosmological probes is to measure the halo mass distribution, number of halos as a function of halo mass, right? The galaxy clusters are exponentially rare. So if somehow you find a very large number of galaxy clusters, that means gravity gravity is very, very important. That has uh, been able to overcome this cosmological acceleration and form a lot of more massive clusters. So you can actually intuitively see that if your dark energy is very dominant, the galaxies are moving farther and farther away very fast with time. So that will suppress the formation of massive clusters, right? Because things are moving away before gravity can pull them closer in together. So massive galaxy clusters at high redshifts can constrain the dark energy equation of state and also sigma 8. So sigma 8 is one of the cosmological parameters in the lambda CDM model. It quantifies the amplitude of uh, density fluctuations at roughly the scale of 8 megaparsec. Okay, it's also related to this CMB normalization parameter. The cosmic microwave background has some power at different k's. Okay, but there is this normalization of that power spectrum which quantifies the amplitude of these density fluctuations in the CMB. That and this sigma 8 are related because the same fluctuations get amplified and are seen as uh, you know fluctuations or the um, over densities at the scales of 8 megaparsec. So the cluster size is roughly a megaparsec. 8 megaparsec is a scale which is actually fairly big. So that's supposed to be still not so nonlinear. That is, they are still in the Hubble flow. Things haven't collapsed and formed bigger halos yet. So this is actually an example of how galaxy clusters are used as cosmological probes. Uh, this is omega lambda, the mass energy density in this dark energy. as a function of omega matter. Okay, and if you just use the cosmic microwave background data, this is what you get as a allowed combination of omega lambda and omega matter. Right? So basically all this is allowed. You can have omega lambda as small as 0.4 and omega matter as large as 0.7, 0.8, right? But if you use type 1a supernovae, right? So type 1a supernovae is this probe that said that, oh, the acceleration, the expansion of the universe is accelerating, right? So these green ellipses are from type 1a supernova data. And the nice thing about an independent probe is that their error ellipses can be like, they need not be aligned. If the errors ellipses here in the 1a data were aligned with this, you could not constrain it much. If they're perpendicular, only the points which are at the intersection of these ellipses is the parameter space which is allowed. Now, this is the use of galaxy clusters as probes. So, you can see it is also an independent probe of this omega lambda. This omega naught is something called dark energy equation of state. How does the pressure of dark energy in these simple cosmological constant models or like simple equation of state models vary as a function of time? So these are the constraints. So this is how people use galaxy clusters for cosmology. So let me actually just show you two examples. Right, so this was this F-gas method, right? I said that galaxy clusters are baryonically complete, right? So if you use that fact, and if you are able to, if you're able to get the mass of the galaxy cluster based on this fact that they are baryonically complete, then you can get the cluster masses. And once you get the cluster masses, you can use them for cosmology. This is a more direct way of using galaxy clusters for cosmology. So what is shown here is the number of halos greater than a mass m as a function of the halo mass. And the red and black are galaxy clusters in two redshift bins. Okay, so this is at high redshift, and this is the present redshift. So with redshift, you expect, things to merge and more massive galaxy clusters to form, and they are doing that. And so this is this is the mass distribution of halos of redshift, in this range. This is the mass distribution at the present time. This is the growth of structure. This is a growth of structure probe of cosmological parameters. And these are the data points. So, there's a little, this is with omega matter of 0.25, omega lambda of 0.35, the Hubble parameter of 72 kilometer per second per megaparsec. And it gives you the sigma 8. So, by varying sigma 8, by fixing these and varying sigma 8, if you use this value of this amplitude at 8 megaparsecs in appropriate units, you get a good fit. And this is this sigma 8 versus omega matter. There is a degeneracy there. So all these things have there are like 7 cosmological parameters, right? And all these different probes have different set of degeneracies. You can get the same observation if you change 2 of them together by a large amount. So that's the degeneracy. So here is the sigma 8 omega matter degeneracy in galaxy clusters. And this is actually what I want to show you as the power of galaxy clusters. So here and here are the same data, actually the same data which is shown here. Okay. This is with the model in which you have omega lambda 0. There is no dark energy in this one. Here is a model where you have omega lambda of 0.75. This is the number per unit co-moving volume greater than halo mass m. So the data points also change. The data points at high redshift change here because the co-moving volume depends on your cosmological parameters. So if this is the number per unit co-moving volume, the data points will correspond to different mass bins. Now, what you can see by eye is that these models of what the number of clusters should be as a function of halo mass at high redshifts is off from the data if you use this value of cosmological parameters. Whereas if you use an omega lambda, which is the standard value now, then the abundance of clusters is matching. Or in other words, if you had a galaxy, if you had a universe in which there was no dark energy, then you should have expected. So if you didn't have dark energy, you should have expected many more massive galaxy clusters, right, than what is observed. So this is where you have 10 to the 14 plus is where you have galaxy clusters. You should have had many more galaxy clusters had omega lambda been 0. But what you see is that that's not the case. You have a different evolution. You have a less number of galaxy clusters. So these are the kind of games that people use. You fix certain parameters and change something else and see whether you get a consistent set of cosmological parameters. Again, it's sort of the game in the town is to be able to get the mass of galaxy clusters. In all of this, you want to get the mass of a galaxy cluster. So what you want to do is you want to calibrate your mass with observables. So observables such as X-ray luminosity, X-ray temperature, and so on. Now, by gravitational lensing, you can get the masses directly. So that's the cleanest way of getting cluster masses. So there are these big surveys of gravitational lensing, and thereby to get cluster masses. So once you have those masses, you can actually make these plots, right? X-axis is mass here. So you need the mass from your observable. So if you have lensing, then you can get the cluster mass. And the more independent probes of these cosmological parameters we have, the better constraints we will have. So all these constraints better give you an intersection point that gives you confidence in the lambda CDM model. If they don't, then something has to be changed. So this is, for example, a mass proxy. This is from cosmological simulations of galaxy clusters. The x-axis is the X-ray temperature, which can be measured by observations, from X-ray observations, from telescopes like Chandra and XMM Newton. And this is the mass. And this is from cosmological simulations, right? And you can actually see that this is a very tight correlation. So if you can model the X-ray temperature, you can actually infer the mass, and then you can do cosmology with galaxy clusters. This is even better, even tighter. Some combination of cosmological parameters, M500, as a function of this parameter gives you an even tighter fit. So your aim is to actually make this as tight as possible. So the x-axis will be an observable. X-axis is something that you can observe, and y-axis is what you want for doing cosmology with clusters. That is the mass. Okay, so I think after we'll actually end here. So this is about the use of galaxy clusters for cosmology. In the next part, we'll continue with clusters and look at the modern ways of studying clusters. And one of the most powerful of them is this Sunyaev-Zeldovich effect. Okay, so that's in the next class.